Good morning. How are you all doing? Tired, quiet, awesome. All right, these are mostly positive. Let me quick ask a question. How many of you guys know what Apache Hadoop is? That's like half the folks. How many people are actually running Apache Hadoop in production today? It's the same half of folks. Okay, all right, cool. So it's good to know. Let me start off by introducing myself. My name is Hsieh. I work at Cloudera. I'm a software engineer, and I'm the tech lead of the HBase team. HBase is a distributed database that runs on top of Hadoop. Kathleen Ting is a technical account manager at Cloudera for one of our largest customers. The co-author of the Apache Scoop cookbook. Scoop is another system in the ecosystem, and a former customer operations engineer. Basically, she's the one that gets called when something goes wrong at a customer's site. Who is Cloudera and what is Apache Hadoop? You guys are mostly familiar with it, but for those who are not, Apache Hadoop is an open source software framework for distributed storage and distributed processing of big data on clusters of commodity hardware. So being at a large installation system administration conference, this is actually one application or one system that really wants to use a lot of machines and make them work together. Cloudera is one of the companies who is providing support, packaging, training, and professional services around the Hadoop software and the software in that ecosystem. We build a distribution, CDH. You can think of Red Hat is to Linux as Cloudera is to Hadoop. And we have worldwide support with folks around the globe. And we've closed tens of thousands of support tickets from our many hundreds of customers over the past 6 years. So here's kind of the outline of what we're going to be talking about today. I'm going to give a summary of the anatomy of a Hadoop system. We'll talk about some of the things that you have to worry about when managing a Hadoop cluster. And then I'm going to hand it over to Kate to talk about troubleshooting and some of the war stories that she's had to deal with our biggest customers. So let's start off with an anatomy lesson. So Hadoop, its mascot is an elephant. So we're really going to kind of do an X-ray of what's inside of this giant elephant. So first and foremost, Hadoop and all of its friends are distributed systems, right? So it's a bunch of processes and a bunch of machines trying to work together as a single process or as a single system. In an ideal world, you'd only have to deal with the heads of the system, and you could think of the entire thing as one giant machine. But in practice, you have to understand and deal with the parts today. There are masters, there are slaves, there are many components, and you have to be able to understand how this thing is put together in order to properly manage and operate it. So what are the tools and what are the things you're going to need? We'll cover the tools and things you're going to need to handle managing these kinds of systems. So let's start from the ground up. What do we start off? We start off with a single machine. And in a Hadoop worldview, a machine is basically the hardware resources, the disk, the CPU, and the memory. It's got a Linux kernel on top of it. And then all of these software daemons for all the masters and slaves generally are written in Java and run in a JVM. And then on top of that, we have a Hadoop daemon. So there's a set of dependencies here. A Hadoop cluster is actually a group of machines. So you'll have a group of machines inside of a rack. And a rack can usually consist of 40 or 20 machines, depending on the size of the blade. And we'll have a top of rack switch, which is another piece of hardware. And together we'll have a rack, and you could have a cluster that's within a rack. You could also have a cluster that spans multiple racks. The largest Hadoop clusters in the world today are on the order of 3,000 or 4,000 nodes, 3,000 or 4,000 machines. So obviously you can't fit that all in one rack. You have many racks. And then beyond that, you can actually have multiple clusters talking through a wide area network, so you have geographic redundancy. So you can have your data in multiple locations in case an asteroid comes and decides to hit your data center. So the Hadoop stack, if we kind of abstract away all the data center parts, is a bunch of machines, right? And we have multiple machines here. And on top of that, we have a bunch of storage subsystems. We have HDFS, which stands for the Hadoop Distributed File System. And it spans all the machines in that cluster. On top of that, we have a system called HBase, which is a distributed database on top that provides highly performant random read-write access. The file system itself has some limitations. It's actually an append-only file system. And then off on the side, we've allocated some machines for coordination and dealing with security. It's kind of the heads for centralized management of security throughout the cluster and centralized coordination. On top of the storage and on top of the communications, the coordination, we have processing engines. Now that we have all this data stored in this cluster, we need to be able to process it. And we have a layer called Yarn, which basically does resource management, manages CPU and memory across these different machines, and doles them out to different processing systems. So there's a batch processing system called MapReduce. There's an in-memory processing system called Spark. There's an interactive query language, query engine called Impala. And there's a search engine, near real-time search engine updates in Apache Solar. So these are all things that take data and process it and either convert it or produce some kind of report for you. These are things that you have to program against. Before you can do all the processing, you have to get the data in and out of the system. So that there are external systems, let's say your web servers, let's say your logs from your application, let's say some different sources of data like your sensors or your application logs. And we need ways of pulling the data in. So we provide two mechanisms for pulling data in. One is through event ingest. So we're writing individual events like a click on a website into Hadoop. And we can use tools like Flume and Kafka for that. And we have bulk loading tools to copy data from relational databases and other data warehouse-like things into Hadoop en masse. These are also the mechanisms you use to get data out of Hadoop. You can use it to potentially take the data that you've transformed inside of Hadoop, reformat it or rejigger it so that it can be served potentially in a relational database system after it's been processed and cleaned up. And then finally, on top of the processing, the integration, and the storage, we have the user interface, things that most users actually work against. So there are languages for doing data processing and data manipulation, and there's a web user interface for entering your queries, browsing your tables, browsing your files, et cetera. And that thing is called Hsieh, the Hadoop user experience. So these are all open source tools, open source languages, open source systems built on top of Hadoop. And many of them are distributed systems themselves, made up of many, many machines coordinating together to get a bigger task done. So here's kind of the overall picture. Really, if you just, instead of looking at all the specific boxes, just look at the colors. Those are the basic layers inside of a Hadoop system. And they're all kind of interacting with each other. So now that we know what a Hadoop cluster is kind of made up of, let's talk about the tools to manage it. So when you're managing a cluster, or you're managing a service, or you're managing anything that needs to stay up all the time, the first thing you have to do is understand normal, right? And this is true if you're managing a single machine, or if you're managing 10 machines, or if you're managing 1,000 machines. You have to understand what is normal. And the way these distributed systems work, most of your information is actually going to come from your logs. And on my team, we're going to make this hat that says boring infrastructure. We want the storage system to be very boring from an ops person's point of view, right? And boring logs are good. Now that we understand what normal is and the things that we expect to see, we can start seeing what is abnormal. And with that, when something comes up or when some kind of problem comes up, we have a thread to pull on, and we can go and look at the different machines or the different services to figure out what's going on. It's also good to see performance numbers so we can compare conformance before and after some event has happened. It lets us isolate the root cause. We've shown the anatomy, so now we have a list of suspects. And now we need ways to interrogate all the different suspects when a problem arises. So what are the things that you use in a basic administrator uses? Well, you need to see what happens, so you use logs. You need to see what the state of the system is currently, so you use metrics from your different services, or you can pull stacks from the different applications. You might want to trigger an event and see what happens when that event happens, so you would like tracing capabilities or an ability to dump what's going on in the system. You want to make sure that things are alive, so you have basic canaries or pings to see if things are still working. And you want to make sure that things are consistent. So if you have a corrupted file system, you want a way of checking that. So you have tools like FSCK in Linux, right? How many of you guys have seen this slide on the right? Yeah, it's a really good slide. It basically, when you're dealing with a Linux machine and the Linux kernel, these are all the different subsystems inside a Linux kernel, and these are all the tools that you would use as an admin to trace, find out information, find your metrics, find your stats, and really kind of figure out which subsystem is making your Linux system run slow. These are really important tools for us too, because part of the Hadoop stack is Linux, right? So really what we have is a couple categories of things that we want to gather, and a set of tools that we can use to get this information out of the Linux kernel and out of our hardware, right? So this stuff is a layered system, and the next layer up is actually the JVM. And the JVM is a whole other system. It's a virtual machine system, and it adds three main things. It adds a just-in-time compiler, it adds threads, a threading model, and it adds garbage collection. I'm not going to talk about the JIT. I'm only going to talk briefly about threads. You basically want to see what threads are going on. If you have a process that has 2,000 threads, something might be wrong. And it's good to see what's going on there. And you can use a tool called JSTAX, which comes as part of the JDK, to get this information. The biggest problems from the JVM usually come from garbage collection. As a developer, you really like garbage collection because it makes the task of writing a program a lot simpler. As an operator, you hate it because it randomly inserts pauses into your servers. And if you care about low latency operations, a 10-second pause is not really a good thing to have. Anyway, to debug this and to find out what's going on, there's a couple command line flags that I really like to add when I kick off my Java daemons, my Hadoop daemons. The first is enabling garbage collection logs. You want to know how much time you're actually spending doing this garbage collection kind of thing, right? So there's a couple command lines to print out the date stamp, which is really important later on for correlating, and printing out information about what kind and how much time you're spending doing garbage collection inside of Java. Another really important thing is getting heap dumps out of the system. And there's a flag that you can turn on so that you can get an object dump of a failed or crashed Java process. What this will let you do in conjunction with the tool I'll talk about later is see what objects are using up all your memory, so you can tell that dev to fix their program. There's another program called JSTAT, which will get summarized metrics versions of how your GC is working. And there's a tool called JMap, and that command line there will basically give you a dump of that program's objects so that you can do analysis and find out where all the memory is being used up. So we have the operating system, we have the JVM, and the next question, the big question is, how do we deal with all the Hadoop stuff on top of it? Yeah, so here's the summary with the kernel and now with the JVM. So what are some of the things that we use when we have lots of machines, right? So we're in a place now where we have multiple machines on our cluster. I would argue the two most popular ones are probably Ganglia and Nagios. You guys use that stuff? No? Yes. Everybody, yes. No? No, you hate it. Pepper data, interesting. Okay, well that's a proprietary tool, so I'm a little biased towards open source, but anyway. Ganglia and Nagios. And these are really good for dealing with the kernel level things and the hardware level things. And with a little bit of elbow grease, it's pretty standard to add JVM kinds of things to it as well. For those who aren't aware, Ganglia is a system that collects and aggregates metrics from machines. It's good for telling what's going on right now and describing normal performance because it uses a system called RRD, round robin databases, to store data and to do roll-ups of historical data. So you'll be able to see what trends looked like last week or last year. And you'll be able to get a very high fidelity of what's happened in the last hour or the last day. Ganglia presents and organizes your information based on a physical resource, based on your machines, based on your RAM, based on your CPU, based on your disk. And then it has really good defaults for monitoring these things inside of a Linux box. So if your problems tend to happen from a particular machine or a particular subsystem on a machine, this is actually a pretty good system to kind of help figure out where that problem is actually coming from. It's good for seeing overall utilization, but it also has some caveats, right? Because it's using this round-robin database, it is lossy. You can't get full fidelity of what happened last week. You can only get full fidelity of what happened in the last hour, right? So things get blurred out. It'll give you the high-level trend, but it won't give you specifics that you might need or want in order to debug a system. It's also fairly dynamic. It's pretty easy to add new machines to the infrastructure. It's a little bit harder to add new metrics, but it's not that much harder. Another system that's popular, our largest customer actually uses this instead of Ganglia, is Graphite. It's actually very similar. It uses black instead of white. Anyway, it's very similar. It handles some of the scalability problems that Ganglia may have had. It has its own round-robin database implementation, and I believe it's better for dynamic metrics than Ganglia is. And then there's Nagios, right? So like, Nagios is kind of health checks and canaries and things that check on basic services. Nagios is generally kind of organized by service. Instead of looking specifically at machines, you're looking to see if DNS is up, if HTTPD is up, or if specific daemons in your Hadoop stack are up. And it's basically, in my mind, the de facto standard for doing this kind of service monitoring. I think the one kind of shortcoming with this tool is it takes a bit of effort to make it work well with Hadoop and HBase and all of the Hadoop stack pieces, because not only are there individual services that we care about, it's a bunch of these services working together with dependencies on other services, and Nagios isn't as good for those kinds of things. So we have tools for the Hadoop stack, but really so far we've only talked about the machines and the kernels of the individual machines. We haven't talked about all the other pieces on top, and what can we use to make that life, make the lives of those people doing that easier. So just like with the kernel and just like with the JVM, there are a bunch of places that you can go inside the Hadoop stack to get your diagnostics, right? To get information out of all these services. But there's a couple caveats here that you have to keep in mind. Whenever a client issues something to a Hadoop system, they're not just talking to one machine. They issue a request to one machine, and it'll probably go issue a bunch of requests to a bunch of other services on the same machine or on other machines. There's shortcuts. There's all kinds of things to try to make this thing efficient. But you're going through multiple layers of the stack in order to fulfill that request. What that really means is there's multiple places in the stack where things can go wrong. Another thing is these systems are evolving quickly. The logs that you had from the previous version will look very different from the logs in the next version. The system is still changing. It's still evolving very quickly. So some of these tricks that you may have for DNS or for HTTP, which aren't changing as quickly, they don't have to worry about the log pattern changing that often. In some cases, the logs have been completely revamped from one version to the next within a year or 6 month span. And then I guess the other really important thing is that these systems are designed to sustain failure, right? The systems are designed so that a failure of a single machine or part of a service will not bring down the entire system or will not lose data. And by design, we're supposed to be able to ignore a lot of these failures. And they generally manifest themselves as performance degradations. It also means it's harder to track and harder to set a proper alert to say this is actually something that matters or something that doesn't. Just like with the JVM, just like with the kernel, we want to be able to get ask a certain set of questions. We want to be able to get logs so we can see what happened. And in this particular case, every daemon has its own log. So we have lots and lots of logs, generally in var log for every particular service. But we have this if we have 1,000 machines times 1,000, right? You have to get your logs from all over the place. We have metrics. Each one of these daemons has a lot of metrics that they provide. And the hard thing is not getting the metrics, but figuring out which metrics actually matter to you. There's a wide variety of them. Tracing, this is actually something relatively new in the Hadoop stack, but we have a way of doing something like strace inside of the storage systems inside of Hadoop. So you can issue a call to the file system, or you can issue a call to the database and trace it. And instead of doing system calls, what we're actually doing is we're tracing RPCs from one machine to another. And this will help us identify which machine or which subsystem is being slow when we issue this distributed request. And then there's liveness. Each of these daemons have web UIs that you generally will ping to see if it's alive. And then there are canaries that you can add to make sure that all the different shards are up as opposed to just the masters. So I've added the third column now. These are the places that you look and the tools that you use to gather information throughout your Hadoop cluster. You have stuff for your kernel, you have stuff for your JVM, and you have a bunch of stuff for the Hadoop stack itself. The star colon means this is usually the web address of the daemons. So you can go to /stacks and get information about what thread stacks are running on there, or /JMX to get JMX statistics. That's generally how statistics are published in the Hadoop systems. You can use htrace. You can go to the web UI. And then, you also have checking tools. Just like the Linux file systems have FSCK tools, the distributed file system has a distributed FSCK for the distributed file system. Similarly, the database has a HBCK, checker for the consistency of the data in the database. So good tools to use as an admin to help find what the root cause of problems are. All right. So we have the Hadoop stack. And the thing is, we have different levels of, that's actually pretty hard to see, but different services provide different information. Some of them provide metrics, some of them provide logs, some of them provide this tracing capability, but each one of them provides its own version of its log. And the hard part actually is, if there's a problem that happens up here when we're issuing a programming language command, tracing and connecting the dots between all the different logs to actually get to your root cause. That's the tricky part. That's the hard part. So the question is, initially what we did is we tried to use Ganglia and Nagios and extend these to handle these kinds of situations. But I think the conclusion that we came to a couple of years ago is that that's not enough, right? These are fault-tolerant systems by design, so failure conditions are more complicated than a single daemon or service going down, part of a service going down. It doesn't understand the distributed services, right? There are programs that are running in the cluster that aren't just running on a single machine, they're running across all the machines in the cluster. It's kind of, instead of slicing by machine this way, we're slicing, we care about tables and we care about jobs going horizontally. And these tools aren't really built with that in mind. These dependencies between all these tools make it actually really hard, and the big questions really end up like, how do we get all the logs? And how do we kind of thread the needle to say, this programming language call caused this thing to happen in the database, which went to the file system, which went to the JVM, which went to the kernel. Like, tracing all those things together is actually kind of difficult because each one of these things produces its own logs. And, we also want more scalability. As we add more machines to the cluster, we end up having to deal with more and more logs. And I've knocked over Ganglia multiple times on its own, so we probably need something more to keep full fidelity of all the metrics that we're capturing about these systems. So what I'm going to talk about now is a bunch of tools that try to address some of these problems. I don't think any of them tackle them completely, but there are several that help quite a bit. One tool is called OpenTSDB. It's an open source and free time series database that actually uses the HBase as a backend. So you essentially now have scalable storage for keeping all your metrics. The really nice thing about this system is that it keeps your metrics at full fidelity for as long as you have space to keep them. So instead of just being able to see what happened in the last hour or yesterday, if you have the storage to keep all the data from last year, you can look at all of last year and see exactly what the Christmas spike or the Black Friday spike looked like. So this is a really useful tool, not necessarily just for Hadoop, but for any kinds of things when you want to keep full fidelity of all your metrics information. It's built on top of Hadoop, though. Another system, and I'll put the pseudo vendor hat on, is Cloudera Manager, but it's actually something that's built to extract all the relevant metrics specifically for Hadoop, specifically for jobs that are running on Hadoop, specifically for workloads running on top of HBase. And it pulls out the things that are kind of the most important. It tracks operational latencies. It kind of pulls pieces from all of the stack, up and down the stack, so that you can get a view of what's going on with your particular job. It's also aware of things like jobs and users and the multi-tenancy things that you have going on inside of Hadoop. Along with that, it provides a bunch of pre-flight checks. Make sure you have things basically configured in ways that make sense and giving you warnings about odd configurations. It provides basic host checks to see, like, is this disk slow? Because that would affect performance. And it does regular health checks or canaries, just like what Nagios would do. It uses an RRD format, so it is kind of lossy on the metrics, but you do have those larger trends like you do in Ganglia. And some other nice things it provides is a distributed log search. I mentioned earlier that all these different services have their own logs, and they're all locally stored on those individual machines. Here you have one place to go, you type in your query, and you can find everything that had to do with that particular, you can search all the logs across all the machines with one pane of glass. We're sort of the Hadoop experts, not sort of, we are, and we've been dealing with support tickets for a long time. We can actually see the logs and find out where problems have shown up in the past, and we can flag things and bring up alerts, kind of like how Nagios would. Point and click, yada, yada, yada. It's free also to use, so it's also quite nice. I didn't really go into much detail, but the goal is to try to cover all of the pieces of the stack and to pull information from all pieces and to help you correlate information from all of them, right? So if you're doing full fidelity metrics, and it doesn't necessarily just have to be for the Hadoop pieces, OpenTSDB is really good for that, and it's relatively easy to add new metrics to collect into that system. So that's kind of this horizontal thing here. If you have logs, I can honestly say probably the best tool out there today is Splunk. You send your logs into Splunk, and it makes it really easy to navigate all of your logs. We have a partner, we're friends with them, so it's actually quite good. And then for managing metrics and logs, kind of having it all in one place, Cloudera Manager, I would say, is probably the best tool. It also does things like manages rolling upgrades, pushing out software to all the nodes in the machine, deploying and provisioning new machines. So it's not just the metrics and the logs part that Cloudera Manager handles. So with that, I'm going to hand it over to Kate, and she's going to talk about some war stories and how these tools that I've described can be used to figure out what the heck is going wrong in a production situation.
Thanks, John. John talked about a bunch of tools that you can use to manage your Hadoop cluster. I'm going to talk about a methodology to use along with those tools and a few case studies. The law of cluster inertia states that a cluster in a good state stays in a good state, and a cluster in a bad state stays in a bad state unless acted upon by an external force. What are some of these external forces? Failures, acts of God, acts of users, things that us admins have to do from time to time, such as upgrades. Hadoop as a whole is meant to withstand these failures. So if you have a job failure, if you have a JVM bug, if you have a slave node that goes down, machine that goes down, hardware that is faulty, Hadoop will be able to keep plodding along, but probably not at the same performance. We might end up missing a few job SLAs. Acts of God, on the other hand, if you have a power failure, if you have a backhoe-induced fiber failure, not so much. Hadoop will basically be brought to its knees, and there are remedies for that, but that's beyond the scope of today's talk. Acts of users. This is why we need security. We need authentication to restrict users, and we have tools for that, LDAP, Kerberos. We need authorization to decide what users are allowed to do. And we also have tools for that. We have Apache Sentry. There's security in Hadoop, security in HBase, and finally, audit abilities. Who did what and when? And we have a tool for that called Cloudera Navigator. And finally, upgrades, although it usually brings in new features, it backports, bug fixes, it's supposed to provide a better and more robust system. Unfortunately, sometimes there are regressions that happen inadvertently most of the time, and we need to evaluate what happened and get to the root cause quickly. And some of the case studies I'm going to talk about today specifically go into more detail about what happens when an upgrade goes a little bit awry. And misconfigurations as well. From my time in support, I've seen that roughly 35% of our critical production Cloudera support tickets are actually due to misconfigurations. And you wouldn't think that a harmless, innocuous misconfiguration could really bring a cluster to its knees, but it can, mainly because there are so many configuration files. For those of you who are running Hadoop in production, you know that there's your core site, your MapRed site, your HDFS site. There are so many configs, and there's so many dependencies between the configs where if you change one config, you need to change the other accordingly. And if you don't, things can go haywire. This is an example of an application pipeline at one of our largest customers. They have a 3-phase pipeline, ingest, process, and export, and they overlap, but these jobs need to finish within a certain time period. So there are very strict SLAs that are attributed to each of these processes. In the first phase, ingest, this is when the data comes into HBase, which is Hadoop's database. The next phase is processing, and that's when the MapReduce job is spawned to run analysis on the data. And finally, the export phase. This is the phase where Scoop, which is a bulk data transfer tool, and we have 2 books to pass out afterwards. So Scoop is used as a bulk data transfer tool to transfer the results, the process results, into an application to serve those results. So our customer encountered this issue where they did a Hadoop upgrade, and then suddenly activity started slowing down, jobs were queuing up, they were missing their SOAs, and they turned to us for help, and they wanted to figure out what is going on. From the slides that John shared, you can see that there are a lot of different layers, and there are a lot of different reasons why anything goes wrong. And you need a quick way and very accurate way as well to determine what is the root cause. And we don't have that much time, so we need to use some sort of methodology to implement a process of elimination methodology. So this is taken from Eric Sammer's Hadoop operations book. He advocates, you look at first at the environment. What is different about the environment? What changed? Did an upgrade happen? Look at the entire stack, because there's a shared dependency on the data center infrastructure. So if there was an act of God and there was a power outage, that could explain some of the issues you're seeing, potentially. Patterns. Are all of the failed jobs coming from the same slave nodes? Could there be some sort of faulty hardware at play? Output. Hadoop tells us what's wrong in their log files. And you want to look, ideally, you want all of your log files to be, as John mentioned, to be boring. Boring is good, boring is normal. But when things go wrong, you want to look for the abnormal things in your log files. Resources. Are you running into issues because you ran out of memory? Is your CPU utilization at the right threshold given the workload you're trying to run? And finally, event correlation. It's important to know in what order things happened, which can often lead to the root cause. So back to our case study. We were able to isolate that the issue was due to the processing phase. And just the fact that we were able to isolate to the processing phase told us what kinds of logs to look for. So the processing phase is when MapReduce is running, and we looked at the slave nodes, known as the task trackers to look at the task tracker logs to see, well, what is going on? Why are these jobs running slower? And sure enough, we see these fetch failures. It comes as an info message, so generally people don't even bother looking at them. There's just so many more fatals to look at, errors to look at, warnings to look at, who has time for infos. But this was actually rather deceivingly innocuous in that with this fetch failure, what it means is with Hadoop, you have a map and a reduce phase, and fetch failures occur when the reducers are unable to fetch the output from the mappers. And that could be, again, due to a whole host of issues. So we've narrowed it down to the map reduce processing phase, but what could it be exactly? And we noticed further that we had users who were running different versions of MapReduce running into these fetch failures. So this told us that this must be something shared across all of these different versions. And further, we noticed that removing the problem node from the cluster seemed on the surface to resolve the issue because the fetch failures would go away, the jobs would start proceeding, the queue would start diminishing, but then the fetch failures would be back and they would be on another node. And so this kind of ruled out hardware issues because restarting issues seem to make it temporarily go away, and then we would randomly see on other nodes the fetch failures show up. So we've eliminated Linux issues, Java issues, hardware issues. We've narrowed it down to the Hadoop daemons. And it turns out that all of the MapReduce versions were running a common Jetty version. And sure enough, there is a Jetty version that is very fetch failure prone. We're able to fix it, patch it, send out a revised, less fetch failure prone version of Jetty to our users. They installed that, and the fetch failures went away. In our second case study, again, we see these slow jobs. So a very similar symptom, but as we'll discover, it's a very different root cause. In addition to the slow jobs, users were complaining about system CPU running at abnormally high 30% given the relatively small workload. It didn't make sense to have such a high system CPU usage. Using tracing tools, we were able to isolate that a majority of the kernel calls were due to virtual memory. And by isolating it to virtual memory, we're able to isolate it to something to do with Linux. And sure enough, since these issues started happening after a Linux upgrade, it turns out that there was a new feature introduced in Red Hat and in some versions of SUSE where this transparent huge pages compaction feature actually interacts very poorly with Hadoop workloads. And as soon as we disabled this new feature in Linux, the system CPU went back to normal levels, the job started progressing again, and we started meeting SOAs, job SOAs again. And finally, our last case study. Again, similar symptoms of slow jobs, but in this case, we were encountering slow jobs at a very precise moment. And I'm sure I'm preaching to the choir here. I'm sure all of you were working on that fateful day in June 2012, where all of a sudden at 5 p.m. Pacific, it just seemed like everyone's clusters became possessed. And for those of us who were running Hadoop clusters, we also noticed that non-Hadoop things like MySQL was also experiencing the same thing. Of high CPU usage, a responsive but slow cluster, and we were noticing that a lot of, we suddenly got 30 or so critical production tickets on one weekend, which is very rare. And they were all saying the same thing, where even though it was a weekend and there weren't a lot of users on the cluster, they were seeing the cluster being used at max capacity. Given that everyone was reporting the same symptoms at the exact same time, we figured we should probably check if there was something to do with timekeeping. And running dmessage showed us that indeed, we confirmed that there was a leap second injection. And sure enough, it was a Linux OS kernel bug. The way that the leap second was handled was handled incorrectly in a Linux kernel, and that was wreaking havoc with not just Hadoop systems, but MySQL and many other systems. And there were websites that were down across the globe as a result of this. And as soon as we reset the time and restarted applications as needed, systems were all back to normal. So we saw a lot of similar symptoms, but very different problems due to Java upgrades, Hadoop upgrades, Linux upgrades. Something that is a common thread through all the case studies we looked at is we had a methodology. We used our tools judiciously along with our methodology to isolate where in the environment, where in the stack, what changed. Is this something from the underlying data center? We're able to pinpoint what the issue is and use process of elimination to very quickly and accurately rule out many areas. And it's also very important to learn from failures. I think that history does repeat itself, and if we don't capture what we've learned for posterity, we are prone to repeat the same mistakes over and over again. John talked about the anatomy of a Hadoop system and the importance of having tools such as Cloudera Manager, that Splunk, that are able to correlate error messages from across the stack. You know, when I talk about the Hadoop stack, when we talk about the Hadoop stack, we don't mean just HBase and MapReduce, Impala, et cetera. We mean the underlying data center infrastructure. So the JVM, the Linux operating system, the networking, all of that comes into play, especially when we need to do any sort of troubleshooting. And it's really important to use tools to determine event correlation, pattern determination, and figure out what needs to be looked at first. We have a full demo cluster available for you to try out for free at Cloudera Live. And if you run into any issues, we have a Cloudera community forum where you can ask technical questions and get answers not just from Cloudera software engineers, but from others in the community as well. And of course, like everyone else, we're hiring. John and I have office hours at 2 p.m. in Willow Room A. We're happy to take questions now, but if you have any further questions, we're happy to answer them at 2 p.m. Thank you. Go ahead, yes.
Hi, first thank you for a good talk. There's a lot of information about Hadoop and Cloudera out there, but it all seems to be oriented towards developers. This is the first coherent talk I've seen about administrating, so thank you for that. But I'm also wondering, are there books that you would recommend or websites that are for the struggling system administrator as opposed to developers?
Yeah, so let's see if I can go back to, so Hadoop operations, which is where I repurposed the troubleshooting methodology.
Is that book still relevant? Because I mean, it's 2000. It came out in 2012. I'm just wondering how much Hadoop has changed since.
So I think the core components are still the same, right? Like this book should cover Yarn, it should cover the file system, and it should cover the basic ingest and HBase systems. The systems that have emerged in the past 2 years are probably Spark, which is an in-memory processing system, and Impala has kind of come out more, and these SQL engines on top. So it's probably a little bit light on those. It really kind of depends. I mean, there are new books coming out for those kinds of things as well, for sure. But like, folks have been operating Hadoop now for, we started 6 years ago and there are people running it already. So there is kind of a dearth, I would say, of people who have a lot of experience of it, but there are classes, there are things out there, lots of resources out there for folks doing this kind of thing. Cool. I do think also that part of what we do and some of what our competitors do is we make it easier for operators to use the system by having all these checks and things.
Mm-hmm. Yeah, I've used the Cloudera management layer is awesome. And sorry for hogging the mic. Just one more. Are there websites or mailing lists you'd recommend?
I mean, the Hadoop user,
Hadoop users,
is
okay.
kind of the common one. That's for the Apache community. There's the Cloudera communities that was mentioned.
Right.
That's more specific for Cloudera distributions. I mean,
Okay.
you know,
Great.
the core Hadoop's going to be the same in most of us, in most of the different distributions, though.
Great. Thank you.
So early on, you made a comment about preferring open source projects for management and monitoring. Why would someone choose using CM over like Mbari as an example?
Yeah. I think for the monitoring Mbari is another open source system for managing a Hadoop cluster. I think that Cloudera Manager is something that has been around longer and is more robust. It handles more things that you would have to do as an admin. So one major feature that is in CM that isn't handled by Mbari is rolling upgrades. Rolling upgrades, if we had more time, we would have talked about it more, but you're doing a rolling upgrade of 15 different systems across 1,000 machines, and you have to kind of orchestrate that process. CM has had the ability to orchestrate these for minor upgrades without any downtime for the past 2 years. And I think this is something relatively new for a system like Mbari. Yeah, does that kind of answer your question sufficiently? I mean, there's just kind of more expertise baked into CM than there is Mbari. Mbari is coming along for sure. Yeah.